Let's use Prolog to describe domino tilings, specifically domino coverings of a chessboard. For instance, we may place a domino tile here, then here, 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 and also on the remaining squares. And we are done. Yes. So we don't even need Prolog for this. On the other hand, maybe we want something more special. For instance, in this specific solution, we can draw a straight line through the board in such a way that it doesn't go through any domino, like this. Such a line is called a fold. And maybe we are interested in fold-free tilings. Do they exist? And so on. Or maybe we are interested in a situation where a few tiles are already placed on the board. And the question is, can such a partial solution be completed to a full solution? Or maybe we are interested in a generalization of the task, where we have tiles with additional shapes, like this tromino or triomino. And in such situations, a Prolog formulation can help us a lot. The only remaining question is, how in the world do we formulate such a task with Prolog? My initial impression is that this is going to be super tedious, because we have to worry about all these geometric aspects, such as the edges of the board, the shape of the tiles and so on. Still, let's try to describe it. What must hold for a domino tiling? It's easy to express in English, right? The chessboard must be covered with dominoes. Obvious, right? But what about Prolog? Well, the good news is that there are dedicated predicates that let us conveniently express such tasks. Especially SICStus Prolog ships with extremely powerful geometric constraints, most notably the geost family of predicates. We can find it online, and here's the documentation. There are other constraints too, such as disjoint, and geost is the most powerful. It constrains the location of non-overlapping multidimensional objects, each of which can take a specified shape. So that's exactly what we need to express domino tilings. Non-overlapping objects. There are also many options and also a usage example. We can also specify rules that must hold, hence the name, geometric constraint subject to business rules, geost. This is an example of a language that lets us conveniently express what must hold. So this is an extremely powerful and versatile constraint described in more detail in a publication. And as far as I know, SICStus Prolog is currently the only Prolog system that provides geost. And we can readily try it with a free evaluation license of SICStus. Of course, it would be nice to have such a powerful constraint available in more Prolog systems. It would likely take many years of dedicated effort to implement it efficiently. But at least a limited subset may be doable within the scope of an ambitious thesis project. And I hope one of you becomes interested in doing this. We can also approach this problem in a completely different way using a Boolean model, because there's a Boolean aspect to placing a domino. A domino either covers a square or not, 1 or 0. And with this approach, we can forget the shape of the board. We only need to think about a sequence of squares, say 1 to 64. And we can model each possible placement of a domino as a sequence of Boolean values, denoting for each square whether it is covered by that placement. For example, suppose we place a domino like this, covering squares 1 and 2. This placement corresponds to the sequence 1 because square 1 is covered, 1 because square 2 is covered, and then 62 zeros, because the remaining squares are not covered, okay? Or as another example, what about this placement? It's the sequence 0, 1, 1, and then all zeros, because it covers only squares 2 and 3. Analogously, this placement is 1, then 7 zeros, 1, and then all zeros. And we do this for each possible placement until the last one, say, all zeros followed by 2 ones for the last 2 squares. And in this way, we obtain a matrix of Boolean values, where each row denotes the consequences of placing a domino at a specific position. Now, what about our task, finding a tiling? A tiling means a choice of domino placements subject to certain constraints. The choice is, for each placement, whether to use it or not. So we introduce Boolean variables xi denoting whether to use placement I. For instance, x1 denotes whether to use the first placement, and so on. There are 112 ways to place a domino on a chessboard, one for each adjacent pair of squares, and therefore there are 112 such Boolean variables in this example, one for each row of the matrix. And each column of the matrix corresponds to one specific square, square 1, 2, 3, and so on. Now, what must hold for a domino tiling? Well, each square must be covered by exactly one domino. This is an exact cover problem, and in this formulation it means that for each square j, so for each column j, if we consider the set of all xi's, where there's a 1 in position ij, so in row I of column j, then exactly one of these xi's must be true. So the arithmetic sum of these Boolean xi's must be 1. Because then the square is covered, and is covered by only one domino. So for example, let's consider column 1. And suppose we set x1 to true. So we choose this placement. Then we cannot also set, for example, x3 to true, because square 1 would then be covered by two dominoes. So either x1 or x3 must be true, or neither of them, but not both of them, because these placements overlap. And thus we have expressed the problem in terms of Boolean satisfiability. We must assign truth values to the variables xi such that certain constraints are satisfied. And with this perspective, the problem is suddenly a lot more interesting, at least to me, because now it seems a lot simpler, to me at least. In this formulation, I don't have to worry about the edges of the board, the different shapes of tiles, the rotation of tiles, or how to even go about searching for solutions. And in fact, it feels as if we have almost eliminated the geometric aspect of the problem. To me, that's a great relief, because I'm terrible with geometry. And personally, I find this combinatorial formulation a lot more appealing. It has a nice and simple uniformity to it, and it also lends itself to a straightforward automated search for solutions. It's a bit strange, because I know it's still the same problem, but it now seems a lot simpler to me at least. So let's formulate this in Prolog. How do we start? Well, first of all, let's use library CLPB, Constraint Logic Programming over Boolean variables. In other words, SAT solving seamlessly embedded in Prolog. This is a quite powerful technology, and the library is available, for example, in SICStus Prolog and Scryer Prolog. And I hope in the near future also in more systems, such as Trailer Prolog. And before we even write any code, let's think about the problem. Notably, how do we represent a tile? Or rather, how do we want to represent a tile? This is completely up to us. We can choose a representation that suits us. And what we want is, of course, convenience. We want to make our lives simple. For example, what about this? A tile is a list of integers denoting the squares it covers. That's very simple and a bit too simple, because a tile extends in 2 dimensions. So what about this? A list of integers. This seems very suitable. It lets us represent domino tiles conveniently, and it also lends itself very well to generalizations, such as trominos. So this is a good candidate to represent various shapes of tiles. And thus we have devised here a language for representing tiles. And at least in my opinion, this is a key task for us as software engineers, devising languages that let us represent our problems. I think this is a really important aspect of software engineering, to find languages that let us conveniently state the problems and also easily adapt and extend the formulations when necessary. For now, we focus on dominoes, and these are the 2 shapes. And we want to describe a tiling of a chessboard, or while we are at it, maybe even more generally of an m times n board. And what is a tiling? Well, in our representation, it's an assignment of truth values to Boolean variables v's. Now, when does this hold? What must hold about v's so that it's a tiling? Well, if rows are the possible placements of tiles, as list of integers, 0 or 1 indicating whether a square is covered, then there must be exactly one variable for each row. So rows and v's must have the same length. This needs the lists library, at least in SICStus Prolog, and we want to formulate a constraint that holds for each column. So it's convenient to reason about the transpose of the matrix. And now we can more easily make a statement about cols, the columns of the matrix. What must hold for each column? Well, the central and in fact only constraint for each column is, as mentioned, exactly one of the pertaining variables must be true. So that's a constraint on the cardinality of true variables. Namely, the cardinality must be 1. Procedurally speaking, we only need to select the right variables, namely those with a 1 in their row, and then constrain the sum for each column. And we describe when this holds for a single column col, a list of integers. For this, it's useful to reason about pairs, where the integers in the column are the keys, and the variables xi are the values. Now, we want a specific subset of these pairs, so we use t-filter. We want all pairs where the key is 1. So we relate all pairs 0, to that subset pairs. And from that subset, we only need the values, the associated Boolean variables. Let's call them c's, because these variables must be constrained. And to constrain Boolean variables with library CLBB, we use the predicate sat. This is the most important constraint of CLBB, and it holds for a Boolean expression if and only if the expression is satisfiable. In our case, what must be satisfiable? The number of true values in c's must be exactly 1. And we can express this with a cardinality constraint on c's. That's the only Boolean constraint we need for this task. Now, to a few predicates we use here. First, for t-filter, we need to reify the truth value of key being 1. And we can do this with equals with 3 arguments from library reif. T is true if and only if key is 1. Next, the matrix. We must relate the board dimensions m and n to a list of rows. If L is the number of squares on the board, m times n, then L is the length of every row rs. And we use findAll to collect all possible rows, one for each possible placement of a tile. Let's now describe what a single row rs looks like. If Ts is a tile, or let's better call it TSS, because a tile is a list of lists. So if TSS is a tile, any tile, then rs means to place TSS somewhere on the board. Since rs is a list, it's convenient to use a TCG for the description. rs may start with a sequence of zeros, then the tile TSS as a sequence of 0 and 1, and then a sequence of zeros. That's a description of rs. A row is a sequence with this shape. However, we need a bit more than that, because each attempted placement starts at a specific position on the board, and the position determines whether we can place a tile there. In the representation we considered before, a position is an integer between 1 and 64. It's a bit more convenient, though, to start numbering from 0, like this, because in this way, the remainders modulo 8 are more useful, indicating the files of the chessboard. So we equip these non-terminals with arguments that let us reason about the position of the placement. The initial zeros go from square 0 to square or position P1. The tile goes from position P1 to P2, and the remaining zeros start from P2. So each of these argument pairs is a position difference relating the current position to the next available position. Now, what is a sequence of zeros? The simplest case is the empty sequence, keeping the position the same. And the other case is a sequence that goes from P0 to P, starting with 0, followed by a sequence of zeros that goes from P1, which is P0 plus 1, to P. Okay? Easy so far. Now the really interesting part, describing the sequence corresponding to a tile. And we recall a tile in our representation is a list of lists of integers. If that list is empty, then we describe the empty sequence, starting and ending at P. And if there's at least one element, a list of integers t's, then we must describe at least that part of a tile going from position P0 to P1. So let's describe that by a non-terminal tile part, yet to be defined. And let's think about it. It's one thing if the tile has only a single such part, like this, such as one of our shapes. Because then we only need to describe a sequence which we can read off, so to say, directly from t's, such as 1 followed by 1 in this concrete case. But it's another thing if the tile has multiple parts. For instance, our other shape has 2 such parts. And this means there must be a sequence of zeros between these parts, because all these squares are not covered. So the sequence we are describing is tile part, followed by zeros, and then the remainder of the tile. And the zeros ensure that the parts are properly aligned. Of course, there can't be just any number of zeros, so we add the condition that the remainder of the tile must start exactly below the current part. So P2 must be exactly P0 plus n, the number of columns of the board. We don't have n available here at the moment, but before we address this, let's really think about it. Because what we just said is overly restrictive. We really must take into account everything that can arise. And what we just said cannot hold in all cases. Because think of this situation. Here we've reached the last row of the board, and so for the last part of the tile, P0 plus n would be greater than the number of squares, and therefore the constraint cannot be satisfied. So in this case, we can only add as many zeros as there are remaining squares on the board. So we say P2 is the minimum of P0 plus n and L, the number of squares. And regarding the issue we noted before, we don't have n and in fact also L available here, and so we make them available. We pass them along as arguments to row, and from there to tile underscore. In the first clause we don't need them, but in the second we do need them, and now we have them available. It's looking good. But sadly, we still have a problem now, because again, we have not considered everything that can happen. Specifically, what we cannot allow is that a part starts, for example, here, and then continues into the next row of the board. Because what we mean with a part is that it's placed in a single row. So we can't completely ignore the geometric nature of the problem. We must rule this out by adding suitable constraints. Unfortunately, I'm also terrible with arithmetic, but with some effort, I managed to find a constraint that I think expresses what we want. We state here an inequality on the remainders of positions P0 and P1 modulo n, and this ensures that P1 is to the right of P0 and not to the left, as in the example we see here. Now, almost done. The only thing that remains is describing one part of a tile that is one list t's, which is simply the sequence denoted by that part of the tile, and keeping track of the position. And that's it. Of course, there may well be room for improvements. For instance, can we make this simpler? I think some of these arguments may not even be needed, and I leave thinking about this as a challenge. Also, we've used a few libraries here, so we import them. This is for SICStus Prolog. And we can also enable the monotonic execution mode of CLB-Z, also for CLB-B. And I leave this as another challenge. So this is our program. Now let's ask a few questions. Maybe start with a very simple case, a 2x2 board. And let's ask, what does the matrix look like in this case? This needs library format for portrait clause. So these are the rows. Let's comment out the output. As expected, each row has 4 elements, one for each square, denoting whether the square is covered by a placement. And there are 4 rows because there are 4 ways to place a domino on a 2x2 board. Now, what about the domino tiling on such a board in general? We get an answer, not a concrete solution, but with variables. And also a remaining constraint on the variables. This is called a residual constraint or residual goal, because it must hold for every solution. And to get concrete solutions, we can use labeling with one argument. This is CLB-B labeling, not CLB-Z labeling, which has 2 arguments. And now we have a concrete solution. That's a tiling of a 2x2 board. The 1 elements denote the chosen placements of a domino. In this case, the last 2 elements are true, and therefore the placements are this, covering squares 1 and 3, if we start numbering from 1, and this, covering squares 2 and 4. This is the first solution, an exact cover of the board. And there's also a second solution, and no others. In this case, the first 2 placements are chosen, covering squares 1 and 2 and 3 and 4 respectively. So it seems to work as intended for this simple case. What about all cases? We can ask about them with the most general query. Are there domino tilings for any M, N and V's? And on backtracking, we get more and more answers, and we see that the residual constraints can become quite involved. So this also seems to work as intended. We get answers for longer and longer lists, more and more possible domino placements on larger and larger boards. And non-termination is of course expected in this case. Whereas for a board with fixed dimensions, we of course want the relation to terminate universally, because there are only finitely many solutions. For instance, for an 8x8 board that is a standard chessboard, we of course expect the predicate to terminate. And we can focus on termination properties by adding false. In this way, only termination remains observable. That is, we don't get solutions, only false if the query terminates. And it takes a while, and eventually we do get false. So the query terminates as expected. What about answers? It again takes a while to set up the constraints, that's expected. But this takes significantly longer than proving universal termination. How is this possible? How can asking for any answer be much slower than showing that there is no solution at all? What's taking so long here? It's the projection of constraints to residual goals in SICStus Prolog and in a current version. Please help to make this faster. We know it's possible because it's much faster in SICStus. And when we ask for a concrete solution via labeling, then we don't run into this problem. It still takes a while, but it finds a concrete solution much more quickly. This is abbreviated. The entire list is this, which is this tiling. And on backtracking, we get more and more solutions. There are many solutions, and here are a few of them. And as mentioned, we don't need Prolog for this, because we can easily find solutions by hand. It becomes more interesting when additional constraints arise. For example, we may say with a lambda expression using library lambda that certain tiles are already placed. For example, let's say that element I of V's is 1 for index 8 and 101. This is the partial solution we've seen before. 2 tiles are now already placed on a board. And using labeling as above, we now get solutions that respect these given placements. So this is already slightly more interesting. Let's take a look at the documentation of library CLBB in Scryer Prolog. Another interesting thing we can do with this library is to select a solution in such a way that each admissible assignment is equally likely. We need to specify a seed so that it's a relation and does not itself behave randomly. For example, in our case of domino tilings, if we simply use random labeling instead of labeling, then it again takes a while and we get from all admissible assignments a uniformly distributed random one. This is quite interesting because to yield a random solution and not just any random assignment, the library must have an overview of the entire solution space. And indeed, the solver in a sense knows all solutions. There's also a predicate called SAT_count to count the number of solutions. The first argument is a CLBB expression, and the second is the number of assignments that make the expression true. So in our case, if the constraints on V's describe a domino tiling, then which expression can we use here to count the number of solutions? We must be careful here to not accidentally add unintended constraints. For example, if we state a disjunction here, then we impose an additional constraint on top of the tiling. This would say at least one of these must be true. And we know, of course, that this will be the case for a tiling. So in our case, this doesn't change the number of solutions. But in general, we must be careful here. So we should state here a tautology, an expression that is always true and also involves all variables we care about. Luckily, we can easily do this like this. This is a tautology, so it doesn't change the number of solutions. It again takes a while, a very long while. Why? Well, we again run into the problem we saw before, the slow projection of residual goals. So even after the solutions are counted, which may even be quite fast, this query takes a long time, because the pending constraints on V's must be converted to residual goals. And as we've seen before, this is currently slow. So how do we prevent this cost? Well, we could manually write the number of solutions and then intentionally fail. And in this way, no residual constraints need to be constructed. So we expect this to be faster. However, there's also a major drawback here. By using portrait clause, we've introduced a side effect, namely output. That's of course not very elegant because showing answers is something that the top level should do for us. We don't want to have to do this ourselves. And also output is outside of what we can reason about within the program. And therefore this makes it hard to test. And independent of all this, we also post more constraints than necessary. Because the disjunction is not necessary to describe a domino tiling, and yet it's here as an additional constraint, even if it's tautologically true. So what can we do to avoid these problems? We have to find a way to state the desired Boolean expression without actually posting the constraints. And where are Boolean constraints currently posted? Only here, with the predicate SAT, which we use only here. SAT appears textually only once in the program, but it is called multiple times as part of a conjunction of goals. And therefore, we can read these multiple invocations of SAT as this must hold and that must hold and so on. So a conjunction. And therefore, when we run the program, we build a conjunction of Boolean constraints, a somewhat implicit conjunction. Implicit because the conjunction doesn't appear as a Prolog term, which we can reason about, but only internally within the Prolog engine, as part of the so-called constraint store, which is managed implicitly by a constraint solver. And we said we want to reason about the Boolean expression without actually posting constraints. In other words, we want to reify the conjunction. This means to make the conjunction explicit as a Prolog term, which we can reason about. That's what reification means, making it into a thing, from res rei thing. So let's take the conjuncts, that is, these cardinality expressions, and turn them into arguments. And now we can reason about these terms. And now we can represent the entire conjunction explicitly as a Prolog term. And it was easy. And that's also a key attraction of Prolog, setting it far apart from plain SAT solvers. Because here we have the full power of Prolog available to reason about the conjunction. We can not only post it, but analyze it, rewrite it, and so on. That's far, far beyond what SAT solvers can do. And since we've introduced an additional argument, we should maybe add an underscore here to indicate there are more arguments for which we don't have dedicated names. And we can now easily express our original domino tiling predicate as the expression described by domino tiling underscore must be satisfiable. So SAT must hold for that conjunction, which is now explicit. Now, for this usage mode, the expression is of course an overhead, because this term must be represented in memory and managed on top of the implicit conjunction, which is also present when we post the constraint, just like before. Luckily, this overhead tends to be acceptable. And if it isn't acceptable, then we can maybe automatically compile it away using partial evaluation, where we ideally at least generate the previous version of the code from this version. And now we've reached our goal. We can now count the number of assignments that make the expression true without posting any constraint, like this. It still takes a bit, but it's now much faster than before, because this posts fewer constraints, and especially because it doesn't involve any residual code projection. What we get here instead is a binding for the generated expression. We don't need to see this if we only care about the count, so we can use a lambda expression to project away uninteresting bindings, like this. Now we see only the interesting bindings. So this is the number of domino tilings of an 8x8 chessboard. Now for comparison, what about the 2x n chessboard for larger and larger n? For an empty board, it's the empty conjunction, and there's exactly one way to make it true, it's already true. For a 2x1 board, we also have exactly one solution, a single domino. For a 2x2 board, there are two solutions, as we already know. For a 2x3 board, there are three, and so on. And what occurs here is a very famous sequence of numbers called the Fibonacci sequence, consisting of the Fibonacci numbers, which appear here as the number of domino tilings of a 2x n chessboard. And we can also use our program to solve variations of the task, such as describing fault-free tilings. This is a special case of a domino tiling. So a fault-free domino tiling must be a domino tiling and additional constraints must hold. What must hold? Well, there must not be any faults. That is, all straight lines through the board must also go through a domino. For instance, to prevent this vertical fault, a domino must be placed in a certain way, either here or here or here or and so on. So we can rule out this fault by requiring that a certain disjunction be satisfied. A disjunction stating a tile here or here or here and so on. And analogously for other faults, vertical and horizontal. So we want to state for each fault line something about the tile placements that prevents the fault. And to rule out vertical faults, we can say there must not be a vertical fault after position 0, 1, 2 and so on. And also there must not be horizontal faults. And I leave this as a challenge. So let's define it. When exactly is there no vertical fault after a given column, 0, 1, 2 and so on? First, let's relate all variables v's to those variables d's that correspond to placements which prevent the fault by covering it. So procedurally speaking, we filter these variables d's as subset of v's. And the fault is averted if any of these variables is true, because then there's at least one tile that prevents the fault after this column. So we state the mentioned disjunction, at least one of these must be true. That's why I called the variables ds, because they are disjuncts. And now we only need to describe the intended subset of variables. Let's use a DCG for convenience. First, if there are no rows and no variables, then it's the empty sequence. And in the other case, if there's at least one row and associated variable v, then it depends. Does this placement prevent the fault or not? So it depends on the squares that are covered by this placement. And let's think about it. What must a row, a sequence of zeros and ones, look like so that it prevents the fault after this column? In our case of dominoes, it must start with zeros, then a domino that covers the fault, and then anything else. So this must be the general shape of the row. And also the domino must be at the right position, of course. It must start at the square just before the fault line. So here we need n again, the number of columns of the board, so we pass along n in an additional argument from above where we have access to it. And now we can refer to it here where we need it. So this is the condition. If this holds, then v is a variable of a placement that covers a fault after this column, and otherwise not. Followed by the remaining variables, described in this way. So this is the sequence of variables that can prevent the fault. We are not completely satisfied with this description because it's incomplete and therefore incorrect in general. And I hope you can express it in a better, more general way. For now, let's try this relation as it is. We start with a termination consideration. For a concrete board with given dimensions, such as 8 × 8, we expect this relation to terminate. And it takes a while, and it does terminate. So that's a good sign. What about a concrete solution using labeling? It also takes a while, and we get the solution. Of course, it's too general. That's not a fault-free tiling, because it has horizontal faults, but at least it doesn't have any vertical faults. And as mentioned, I leave finishing this as a challenge. Now, regarding CLPB itself. Internally, the library uses a very interesting data structure called binary decision diagrams, BDDs. More precisely, reduced and ordered BDDs, RO BDDs. BDDs date back to Shannon, and RO BDDs were introduced by Randall Bryant in 1986 in a very famous paper. For a time, this was one of the most cited papers in computer science. And nowadays, when we say BDDs, then we tend to mean this variant, that is, that they are ordered and reduced. BDDs are now heavily used in circuit verification, model checking, and so on. The idea of BDDs is to represent the entire truth table of a Boolean function as a graph, a directed and acyclic graph. For instance, the cardinality constraint, where we say exactly 2 of x, y, and z must be true, has this BDD. And for this variable order, only this BDD, because ordered and reduced BDDs are canonical. And it's not a tree, because there are nodes that have multiple parents, but it's a directed and acyclic graph. And this is what makes the representation so compact, that different nodes can point to the same shared node. And from this BDD, we can read off the truth value of each assignment. We only have to follow the edges, starting from the root, x in this case, and following either the dotted or the solid line at each node, depending on the truth value of the node's variable. And note how compact this representation is. Contrast it, for example, with a Boolean formula in conjunctive normal form for this condition. And there are also other variants of BDDs. A very famous one are zero-suppressed BDDs, called ZDDs, introduced by Shinichi Minato. They are especially useful for sparse functions, that is, where in solutions only comparatively few of the variables tend to be true. And also in this case, the ZDD uses even fewer nodes than the BDD. So it's an even more compact representation of the same function. And there's also a ZDD-based variant of library CLPP, which is a lot more efficient in certain cases. For example, Domino Tilings tend to benefit from this. And the size of the graph depends on the function we want to represent, the type of BDD we are using, and also on the order of variables we choose. And as a consequence of using BDDs, CLPP has a few properties that are quite unique for a constraint solver. Maybe most strikingly, due to using BDDs internally, CLPP has at all times an overview of all existing solutions. And therefore, CLPP is complete. Not only in the sense that it finds all solutions, which we of course take for granted, but also in the sense that it derives all consequences of posted constraints. And therefore, as we said, SAT succeeds if and only if there's a solution. The only if sets it apart from many other constraint solvers. And therefore, posting a SAT constraint can be very expensive, because determining whether a Boolean expression is satisfiable is famously NP complete. That's a contrast to CLBZ constraints. Integer constraints are of course even harder than Boolean constraints. In fact, integer equations are not even decidable in general. But posting integer constraints tends to be very fast. The search is often tough when using CLBZ, but posting constraints is usually fast. The reason why posting SAT can be slow is that a BDD can become very large, exponential in the number of variables. And therefore, constructing it may take exponential time. It may also take much less space and time. And that's a key attraction of BDDs. Many formulas have reasonably small BDDs, and then it pays off to use them. So our hope when using CLPP is that the involved BDDs turn out to be small. And the way we write our code can also have an impact on the size of BDDs. In addition to the order of variables, the order of constraints also matters. That's another difference to CLBZ, where the order of constraints doesn't matter as much. And after all BDDs are constructed, and that can be a very long after, but after they are constructed, we can do a few interesting things very efficiently. Maybe most notably, we can determine satisfiability of all constraints in constant time. We only need to check whether the BDD is the node false. And if it's not, then the constraints are satisfiable, because BDDs are a canonical representation, and so all unsatisfiable constraints have the same BDD. We can find a solution in linear time in the number of variables. That's also extremely efficient. It's as fast as possible. We can count the number of solutions by performing arithmetic operations for each node of the BDD, involving enough bits to represent the numbers. So the dominating factor is the size of the BDD, and therefore this can be vastly faster than enumerating all solutions. And after counting, we can speedily select a uniformly random solution. We can also efficiently solve a linear Boolean programming problem, that is, maximize or minimize a linear expression subject to constraints, and so on. And these features make BDDs a very interesting data structure. And therefore, we can solve quite complex problems with CLPP. For instance, there's an unimaginably large number of ways to cover a chessboard with monominos, dominos, and trominos. Here's a sample solution picked at random. And with CLPP, we can compute this number very fast and also solve many related tasks, such as counting the solutions that are fault-free, or in which no congruent tiles are adjacent, and so on. Very tough counting tasks. But CLPP can't solve everything, at least not efficiently. And what do we do if CLPP is too slow? Well, one very straightforward approach is to give up, because Prolog is slow, right? On the other hand, we know that SAT is NP-complete, and therefore we cannot expect fast solutions for all instances. Also, all approaches will likely run into hard instances, hard for them at least, maybe easy for others. And often the only way to find out what works is trying it. Of course, we may have or develop an intuition for what's likely to work, but in general, we need to try it. We don't know in advance. And there are many things we can try. For instance, we can try different orderings of variables and constraints. For example, let's look at how we describe the rows of the matrix. A very simple change we can make here is to sort the rows, say lexicographically. This is a very small change, which nevertheless has a measurable impact on performance, because the order of constraint variables matters for CLPP. So I suggest you try it. And also other variants, such as what about reversing the list and so on. Another thing we can try immediately is the ZDD-based version, which we already mentioned. ZDDs can represent such domino tilings very compactly, and they are more efficient than BDDs in many examples. We can of course also try to improve library CLPP itself. The Scryer version is currently written entirely in Prolog. That's of course a good motivation to make the Prolog engine fast. It heavily uses AVL trees to represent BDDs, and therefore it will automatically benefit from improvements to library SOC, which is a good candidate for cheat compilation, because it uses only quite basic predicates internally. Even better would of course be a data structure with asymptotically higher performance, because currently we pay logarithmic overhead for AVL trees. Hash tables would improve this. Or maybe typed nodes or edges would improve performance. SICStus Prolog does this. Or for example, the library could automatically try to reorder variables to make the arising BDDs more compact and so on. It's also worth considering to move a few BDD operations to Rust for higher performance. On the other hand, this would render the library less portable to other Prolog systems and also reduce the motivation to make the engine itself faster. And improving library CLPP, possibly with these ideas, would be a very sensible scope for interesting thesis projects. It has more room for experimentation, and it's also conceptually simpler than implementing the geost constraint, which is very tough and a long project. So I hope one of you becomes interested in this. Another thing we can try is to simply forget BDDs and use CLPZ or other solvers instead. There are many kinds of SAT solvers and not all of them are BDD based, and many other things we can try. The good news is that Prolog makes it easy to try different things, different orders, different models, different solvers and so on. One of the reasons for this is that CLPP is a very high level interface to BDDs, and this keeps Prolog programs that use it short and easy to change. BDDs are used internally, but the interface, at least in Scryer Prolog, only provides predicates like SAT, SAT count and so on, which operate on Boolean formulas, not BDDs. On the one hand, that's an advantage, because it allows changing the implementation of the library while keeping applications the same, because applications only use the interface of the library. So it's currently possible, for example, to change the entire library to a completely different approach, such as local search or backtracking search, or to add lazy clause generation and so on, and existing applications would still work. Some may be slower than now and some may be faster. On the other hand, this high-level interface can also be a disadvantage, because some applications would maybe benefit from more direct use of BDDs. And maybe the library should provide interface predicates for reasoning about BDDs too. SICStus does this, for example. This would yield applications that are more dependent on a specific implementation method of the library. So that's an interesting design question involving a trade-off between freedom and features. The key question is, how deep into the engine should Prolog applications be able to look? Do we want to expose the internals of the solver and thus cement its approach? Or do we want the internal approach to remain abstracted and therefore changeable? And there's also a maybe even deeper trade-off here, a trade-off between encouraging computation or creativity. Because on the one hand, CLPP is a very powerful technology, and it can solve many interesting problems purely by computation. That's a relief, because it means that we don't have to think so much. And this may motivate us to say, it's good to give applications total control over BDDs too, because then we can delegate even more tasks to the library. On the other hand, thinking can massively reduce the need for computation. And so we may also want to encourage thinking. And lower level primitives and even CLPP itself could detract us from this. As an example, consider the so-called mutilated chessboard problem. This is a chessboard where two opposing corners are not available, say this one and this one. And the question is, can the remaining squares be exactly covered with dominoes? No. And CLPP can prove this with computation. There's also a different way to see this. The key insight is that placing a domino always covers exactly one white and one black square. And in this example, two white squares were removed from the board. This means that there are now more black squares than white squares, and therefore we can't cover the remaining squares, at least not exactly. So this is an example where genuine insight can save a lot of computation, and we can't expect such a creative act from CLPP, even though it can help us a lot with many hard tasks. And such insights also don't come easy, at least not always. Some problems are simply inherently hard. And for some problems, we need to combine everything we have. Genuine insight, computation, and also try many different things to solve them.